Today I'm going to give a brief overview of proximal causal inference. So before I came here, Dr. Ken Rice told me that I need to, because this is the first seminar of the quarter, I want to make sure that the material is accessible. I try my best, but if you have any questions throughout the talk, feel free to interrupt.
What is this?
Let's see. Are you the host?
Wait. Oh, do I need to leave on my phone?
Your phone on your phone.
Surely.
All right, thank you. So now I'm affiliated with Department of Biostatistics, St. Jude Children's Research Hospital. Before I came, my department chair gave me an assignment, that is to tell you guys we are hiring. We are hiring biostatisticians at all levels, and St. Jude is listed #1 of multiple best employers list in 2023. So if you're interested, if you're in your final year of either master or PhD program, this is an opportunity you don't want to miss. Okay. All right. If you can remember anything else from the talk, this is one thing you want to remember. So today I will first give an overview of proximal causal inference. This will be a part mostly about other people's work, but a short history of proximal causal inference, my idea is quite fascinating. And then I will introduce two of my recent projects. So one substantial challenge in causal inference is that many of the analyses have the concern of latent factors, which can cause additional bias. So here I'm showing the relationship between variables using the directed acyclic graphs or DAGs. I use A to indicate exposure of interest and Y to indicate the outcome of interest. We usually are interested to make estimation or inference about the effect of A on Y. But if there is a latent factor U that is the common cause of both A and Y, we run into the familiar issue of unmeasured confounding bias. So it may cause suspicious bias in our estimates, and it may also distort the existing association between A and Y. If the unmeasured confounding bias exists, the observed association do not represent the causal effect. Of course, there are all sorts of other situations where the latent factor may cause bias. In some scenarios, in the presence of a mediator, we may want to estimate both the directed effect or the indirect effect mediated through this mediator. But if there is a latent factor that is the common cause of these three variables, both effect estimates will be biased. In rare occasions, we also want to estimate a mediating the indirect effect mediated through an unmeasured mediator, which is very rare, but sometimes it happens. And finally, we may have the time varying treatment. And in this case, we have the more complicated form of time varying unmeasured confounding. So in this talk, I will actually focus on the simplest case of just one point exposure and point outcome, and you have time varying. You have this one unmeasured confounding bias. But in each of the scenarios, there is one proximal causal inference method being developed in the past to address such bias. So unmeasured confounding bias is quite ubiquitous in epidemiological research. Most concern is confounding by underlying health conditions, health behaviors, or access to healthcare. The standard practice in many epidemiological research is to collect covariates exhaustively including disease history, lab measurements, perceived health from surveys, past physician visits, etc. But residual confounding bias may still remain. This may be because important confounders may not be collected, especially if an analysis was not planned ahead, such as in post-hoc analysis of cohort studies, or if the collected covariates are subject to measurement error, such as recall bias or underdiagnosis bias. And finally, collected covariates may not reflect the complex nature of the intended confounders. For example, sometimes distance to a clinic or living in an urban versus rural area are used as proxies to access to healthcare, but they are not precise measures. And in short, collected covariates are at best noisy measures of the true underlying confounding mechanisms. As an example, I will use the right heart catheterization studies. Connors et al. Studied the effectiveness of RHC among the critically ill patients in a prospective cohort study. They found that patients who received RHC treatment had an increased mortality. So RHC is a device, basically a device that put in your heart to monitor your cardiovascular conditions in order to facilitate subsequent treatment. Only very ill patients may receive this treatment. So this observed increased mortality may be due to confounding by, at least partially due to confounding by frailty, because patients with acute heart conditions were more likely to require RHC. Another very famous example of formation confounding in epidemiology is the effect of seasonal influenza vaccine on mortality among the senior. So in many observational studies, it has been found that seniors who receive influenza vaccine had substantially lower risk of death and hospitalization during influenza season. But a recent study also found that they have the lower mortality and pneumonia hospitalization even before the influenza season. That is the period when the vaccine should have no effect because the virus hasn't started circulating yet. So this suggests that the observed association during the influenza season may be at least partially due to the confounding bias because of the recipient's healthy behavior. It might be the seniors who receive the influenza vaccines are more likely to adopt healthier behaviors, so they have lower mortality. Now, in this particular example, mortality and hospitalization before influenza season is a particular example of negative control outcome. Okay, thank you. Now comes the very important concept of negative control methods. So this general approach has been used in lab experiments or epidemiology studies from like very long ago. In 2010, it was formalized in a paper by Mark Lipschitz and my postdoc advisor, Eric Chedin and Cohen. So they basically summarized two types of negative control variables. The first type is a negative control outcome, which is a variable that is not directly affected by the exposure of interest, but the confounding bias between AW and AY are comparable or almost identical. The other variable is negative control exposure, which is a variable that does not have direct effects on the outcome of interest, but the confounding bias between ZY and AY are comparable. So here, the requirement that the confounding bias are comparable between the negative control variables and the primary control variables are termed U comparability. And it is a pretty strong assumption. So the negative control variables can be used to detect confounding bias, because in this case, if you found an association between AW in your data set, it must be because of the confounding bias at play. Similarly, if you found an observed association between ZY, it's also because of the confounding bias. This is a result of U comparability. Also, you may use it to correct a bias, because the magnitude of the bias may be estimated assuming U comparability. U comparability is the basis of many early methods utilizing negative control variables for bias correction. But yeah, as I said, it's a pretty strong assumption and hard to verify in practice. Now, negative control variables are usually abundant in public health research. For example, so the suitable negative control variables also depends on what unmeasured confounding is of most concern. If the most concerning unmeasured confounder is healthcare seeking behavior, NCE can be the health habits, annual physical exams, ophthalmology visits, etc. If U is frailty, then NCE can be medical supplies, physician visits in the past few years, etc. A very particular example is instrumental variable, including genetic variants. So the SNPs, or genetic variants commonly used in Mendelian randomization studies, are also valid NCEs. And more importantly, some SNPs, or genetic variants, or instrumental variables may have some assumption violations. So they may be invalid IV, but they can still be valid negative control exposure. And NCO can be injuries, certain lab measurements, or for in the previous example, for vaccine effectiveness studies, it can be mortality or health outcomes outside of the circulating season or unrelated post-exposure physician visits. Now, the most groundbreaking work in proximal causal inference is actually the development of negative control methods. So although now when people think about proximal causal inference, they might think of my postdoc advisor, Eric Chen, but the pioneering work is by two authors in 2014, Kuroki and Pearl. If you know this name, Pearl did a lot of work in graphical models for causal inference. So they considered a pair of proxy variables to the unmeasured confounding for effect restoration due to measurement error. They specifically considered the discrete variable or linear structural equation setting. They are also among the first ones to specifically use the term proxies. Now let's see how double negative control method works in comparison to the single negative control method. Here, let's assume that everything is linear. Make it very simple. So we have the distribution, we have the model of the outcome on the other variables. We have the model of the negative control outcome on the other variables. And we have the model for the unmeasured confounder on all the other variables. So you can use a pen and paper, and by a very simple iterative expectation and a little bit of algebra, you can show that beta A, which is the effect of A on Y in the first model, can be recovered by this very simple two-stage least square algorithm. In the first stage, you regress W on A, Z, and X, and you obtain a predictor of W, which is W hat. And in the second model, you can regress Y on the other models. So the regression coefficient of A will simply be the beta A, the effect parameter of interest. Here for this two-stage regression to work, two very specific conditions are that in the model of W, the regression coefficient for U shouldn't be 0. should be non-zero. And also for the model of U on AZ and X, the coefficient for Z should be non-zero, indicating that both W and Z should be associated with U. This is the U relevance condition. Compared with the U comparity condition, this is considerably weaker. Now, this part is more challenging, so I will not go into much detail. But beyond linear, even beyond the linear model setting, the double negative control method can still work. So here we're putting restriction on the outcome model and treatment mechanism. So here we have a specific concept called confounding bridge functions. We have a outcome confounding bridge functions, which puts restriction on the outcome distribution. And we also have the treatment confounding bridge function, which is related to the inverse propensity score. So the mean potential outcome can be recovered by either confounding bridge functions. So you see that here we are not invoking any of the parametric assumptions, which suggests that with double negative control variables, you can non-parametrically identify the causal effect. In practice, though, to estimate the confounding bridge function, there are like multiple approaches. One approach is that although ATE is non-parametrically identifiable, you may just put parametric assumptions on the confounding bridge functions anyway. Or you may also use non-parametric methods, such as spline models or kernel machine learning methods. So actually today, when I meet with Andrea and when I meet with other people, a new concept I learned is that these estimating equations are weakly identified. You don't have much information to make inference about the Q and H. So there are multiple ways of improving the inference, and there are also limitations on that. So I'm very looking forward to reading more about it. Now here comes the final concept of proximal causal inference, which is a collection of methods that aim to correct bias due to a latent factor, leveraging proxies to the set latent factor. Beyond the point exposure and outcome setting, the proximal causal inference has also been extended to time to event data, longitudinal data, time series data, or outcome-dependent sampling data. And also it has been extended to proximal mediation analysis, or to study, to correct the bias due to latent common causes for event time and right sensor indicator in survival analysis. Yeah, I missed another work here. So Gary actually also has a work on mediation analysis using proximal causal inference. So any questions? Okay. So now the first project I'll go into detail is the regression-based proximal causal inference for right sensor time to event data. So I introduced the confounding bridge function approach, but to do it, you have to solve these complicated integral equations, which kind of prohibits the routine application of proximal causal inference. So some of Eric's recent work focuses on if there are like more straightforward application of these methods, which people can understand. So one previous work is this proximal two-stage least square approach. In the linear setting, it's very easy. I have introduced it, but it can also be applied to the setting where the outcome model Y and the NCO model W follows log linear model. So you basically do a similar two-stage least square approach as I introduced before. But for right-censored time-to-event data, it's a little bit more complicated. So the most general case has been studied previously, but they still focus on estimation of marginal survival curve, and their method involves solving complex integral equations. The goal here is to develop a similar two-stage least square approach to facilitate the routine application of proximal causal inference. So our goal is to develop a method which is able to adjust for measured confounding even in very limited setting and accommodate different types of NCOs and easy to implement. So we are making numerous parametric assumptions here. Of course, that's a huge price to pay for convenient computation and modeling. So I'm introducing this project for you guys. It's mainly as a math exercise. So I'll introduce some standard notation. Here, C is the censoring time, T is failure time or event time of interest, U is unmeasured confounder, and A is the exposure of interest, X is time-independent covariates, W and Z are negative control outcome and exposure respectively. And T tilde is the censored event time. I will use lambda to denote hazard function and S to denote survival function. So for the two-stage least square approach to work, I assume additive hazards regression model. That is the outcome hazard, the conditional outcome. Sorry, the conditional hazard function of the event time follows a linear structure of the unmeasured and measured confounders and the exposure. So I am not invoking the familiar Cox proportional hazard model here. The main reason is that the math simply doesn't go through. So a feature of additive hazard regression model is that the survival function will be on the multiplicative scale, which is different from the Cox proportional hazard model. For Cox proportional hazard model, the survival function is on the log scale. If you look at some other methods, such as mediation analysis or IV methods with survival outcome, additive hazard model is also the correct model of choice. Now, if the exposure is binary and if some standard causal inference assumptions hold, then the additive hazard regression model also indicates that the ratio of potential survival functions is can be inferred is related to this beta A. So in this additive hazard regression model, beta A is the causal effect of interest, and it is the conditional hazard difference. Now we are, as before, we are making the standard negative control variables assumptions. We are assuming that the exposure and the outcome, the exposure and the NCO are conditionally independent, and the NCE and the outcome and the NCO are conditionally independent. So again, for the math to go through here, I invoke two pretty strong assumptions. One is that the arrow term in the unmeasured confounder is exogenous. It's independent from everything else. And also the mean model of the unmeasured confounder follows a linear model. And as in the standard literature, I assume the sensory mechanism is conditionally independent. in the conditionally independent sensory. So here you can, so by the previous assumptions, you can recover the outcome hazard function like this in terms of the conditional expectation of a measured confounder on the measured variables. So here in the first line, the right-hand side is mostly measured, but you still cannot identify beta A because A is in both the components of this term and this term. So essentially, it is saying that the confounding bias is mixed with the true treatment effect, and without external information, you cannot separate that out. I will, so here I will make another additional assumption that the NCO follows a linear mean model. Then you can simply take iterative expectation and see that the mean model of the NCO can also be expressed in terms of expectation of U given AZX. And then you come down to these two equations on the event outcome and the NCO. So here, for the above equations to have a unique solution for beta A, you need a U relevance assumption, which essentially says that CU1 has full row rank, and which essentially says that U is associated with both U, W, and Z. So the negative control variables are relevant to the unmeasured confounder. So now the nice thing about these two equations is that everything is observed. The unobserved U, when you're projecting it onto the measured variables. So in the linear case, you eventually comes down to these two linear or this is a linear model and this is a additive hazard regression model. Solving these two regression model, you get the regression coefficient for A in the second model, which is the causal effect of interest. So yeah, if you're not following me, eventually all I did was to reach this simple two-stage least square algorithm. So here you first regress the NCO onto the observed variables A, Z, and X, and you obtain the linear predictors. And then in the second stage, you replace the unmeasured confounder with this linear predictors in the first stage, and the regression coefficient for A is simply the estimator of your causal effect. So I will skip the case of a log linear model. I will skip the case where NCO follows a log linear model or NCO follows an additive hazard regression model, but the result is the same. You can estimate beta A using simply the combination of two regression models. And if you have multiple NCOs, it's very similar. You just fit the corresponding model for each entry of the vector of W, and then you fit an additive hazard regression model on basically everything. Now, the benefit of including multiple W is that now for W to be U relevant, you just need this vector to have full row rank, which is a weaker condition for each of the entry to be full row rank. So it means that if you have multiple W, you will be able to adjust for a measured confounder of a higher dimension, which is also quite intuitive because having more NCOs should allow you to capture more variation in the unmeasured confounder. In R, the implementation is very easy. In the first stage, you just use the GLN function to regress W on A, Z, and X using the corresponding family. And you obtain the linear predictors. And in the second stage, you just fit an additive hazard regression model. Now I will skip the simulation setting. And I will compare three methods. One is the proposed two-stage least square method. The other is we only adjust for the baseline covariance X. The third method is we adjust for both X and the measured proxies of this unmeasured confounder. The third method is also the most often used in practice. So we see that the naive method is pretty biased, and even the fully adjusted method is subject to some bias. But the proposed two-stage least square method is essentially unbiased, which is not surprising because we simulate the data in a setting that it works. And also the confidence interval, 95% confidence intervals of the two-stage least square approach perform pretty well. However, when the negative control variables is not that associated with the unmeasured confounder, or your association is essentially zero, the bias is larger and the 95% confidence interval is less calibrated. So going back to the RHC study, where we study the association between RHC treatment and mortality. We use the lab measurements as negative control variables. These lab measurements all give some evidence of the healthiness of the participants. And using the two-stage least square approach, the estimated hazard difference is smaller than the alternative methods, but it doesn't reverse the conclusion that RHC is harmful. So now the proximal two-stage least square approach is available as an R package, but there are still substantial challenges, such as selecting negative control variables if multiple candidates exist. So the manuscript is submitted, and there are several other work. Most substantially, we want to further look at time-varying effects of covariance. Any questions? Okay. So now the third project I'll be introducing is proximal causal inference framework of synthetic control. So synthetic control is now is a popular method in panel data. So here the example is to study the effect or the impact of German 1990 reunification on their economy. The outcome is the per capita GDP. So the exposure is the 1990 reunification. But the problem is that we only have like one country, West Germany, that has the treatment. So it is different from the standard RID scenario. Now, a method that people use is synthetic control. So ideally, to calculate the causal effect, you want to have two very similar countries, West Germany and a control Germany, say control Germany. And control Germany doesn't have the reunification. And you compare their per capita GDP post 1990 to get the outcome. But obviously, it's very hard to find this control Germany. So what the synthetic control methods does is they use a weighted average of the outcomes of multiple countries to match the outcome of Germany during the pre-treatment period. And they use the difference of West Germany and the weighted average to get a causal effect. So the synthetic control framework is quite intuitive and easy to communicate the results, but it's also mysterious in the sense that it's unclear why and when it is expected to work. And we also want to place the synthetic control framework in a standard causal inference framework, in the sense that we want to have a clear definition of the causal contrast of interest, and we want to conduct inference on the causal effect of interest. So the main progress in this field has been made by Abadi et al., and they have a lot of work in this area. But most of their work assume a perfect match of the pre-treatment outcome. Our goal is to provide a theoretical synthetic framework that allows for imperfect pre-treatment match. So now let's go into some math details. So suppose we have n+1 units. So we denote the units by I equal to 0 all the way to n. I equal to 0 indicate that the unit that will eventually receive the treatment, and the other units are the control units. And we have big T time points. So we will consider the interactive fixed effects model in that we assume the outcome is subject to the influence of a latent factor lambda t. So here I assume that we assume that the potential outcome of the treated unit under no treatment follows this factor structure. And for the untreated unit, so because they never received the treatment on the treated unit, WIT of 0 and WIT of 1 is equal, and they also follow a factor model structure. Is this clear?
So W is different, is a different variable or?
Oh, sorry, I use W to indicate the outcome of the control units. So the control units here, the potential outcome is the outcome of the units where the treated unit receive or not receive the treatment. That's why the treated unit receiving the treatment does not affect the outcome of the control units. This is also a no interference assumption.
Sorry, the 0, what is I in the 0?
Oh, I use I to indicate the units. I equal to 0 means it's the treated unit.
So it's the same as YT?
Yeah, it's the same as YT.
Otherwise, you could have said Y sub I equals 0, right?
Oh, yeah.
Sorry.
Yeah, sorry. Here the notation is a little redundant. I only have one Y, so yeah. Thank you. So I will also assume that the arrow term is exogenous in the sense that its conditional expectation on the latent factor equal to 0. So I will define the treatment effect as the difference between the potential outcomes, which is also the treatment effect on the treated unit. So here, the treatment effect is viewed as random. I will assume consistency, which means that for the treated unit, the pre-treatment outcome is equal to the potential outcome were they not receiving the treatment. and for the control units, it's just this. And for the post-treatment area, the observed outcome of the treated unit is the potential outcome were they receiving the treatment. And for the control units, it's just this. So with the consistency assumption, you can connect the observed outcome with the potential outcomes. Now, the goal of synthetic control methods is to find a set of weights that match the pre-treatment outcomes between the treated unit and the synthetic control. The rationale is that in the pre-treatment period, the factor structure of the treated unit and the control units will eventually match. We are hypothesizing that the variation in the outcomes is mainly driven by unmeasured confounding. So matching on the outcome is approximately matching on unmeasured confounding. Now, this assumption is mostly reasonable if the residual error in each outcome is negligible. Then matching on the outcome is equivalent to matching on the unmeasured confounder. Otherwise, these two might mean quite different things. So we may have multiple candidates of the control units, but in practice, not all the control units are similar to the treated unit. Abadi suggested that we only select the units that is sufficiently close, similar to the treated unit into the synthetic control unit. So after this selection, we will have a pool of control units which contribute to the synthetic unit. We will index it by D. So Abadi assumes that in the pre-treatment period, the outcome of the treated unit and the synthetic control unit are identical. So when the pre-treatment outcome fit is when the pre-treatment match is imperfect, the synthetic control method is discouraged from using. An alternative assumption by Furman and Pinto in 2021 is to say that instead of matching on the outcome, we assume matching on the factor structure. So there exists a set of weights that the factor loading of the treated unit is equal to a weighted sum of the factor loading of the control units in the donor pool. So the unmeasured confounding effect on the treated unit can be matched by that on a weighted average of the donors. Now, under the interactive fixed effects model, we can express the outcome of the treated unit in terms of the weighted sum of the control unit outcome plus an error term. If you look at it, it's just a simple linear regression. So one may be tempted to estimate the synthetic control weights, which are the alpha here, by regressing YT on WIT. The standard synthetic control method can be viewed as the constrained ordinary least square assumption, where they put additional restraint that the sum of these synthetic control weights are all positive and sum up to 1. But if you look at the error term long enough, these epsilon IT are the error terms coming into the regressors. So the error term here is correlated with the regressor, which violates the condition that that ordinary least square give you unbiased estimates. So here we propose an alternative assumption. We assume that the outcome model, we assume that instead of exact matching, the expectation of the treated unit outcome is equal to the expected outcome of the synthetic control unit. So additionally, if we observe a proxy of lambda t denoted as zt, which is independent from the primary and active control outcome variables, then again, by simple iterative expectation, you can show that this equation holds. So in this equation, everything is observed. By solving this integral equation, you will be able to estimate the synthetic control weights alpha here. If you remember what we discussed previously, this is simply the proximal causal inference frame. Therefore, we can reduce the problem of synthetic control estimation back into proximal causal inference. So now for the proximal causal inference approach to work, in addition to the standard assumptions of classical synthetic control method, we also need the additional assumption that the proxies to the unmeasured latent factors exist. Then if these assumptions hold, both the synthetic control weights and the average causal effect can be identified. First, we estimate this synthetic control weights by solving this integral equation. And in the second step, we can estimate the average causal effect by the expectation of the treated unit outcome minus the synthetic control unit outcome. So I will expand on these two steps in more details later. Now, for the first step, we want to solve this integral equation. One easy way is to simply solve this estimating equation. So if you multiply a zt here, its expectation is still 0. So this is an unbiased estimating equation. And we can estimate the unknown parameter of I here by the standard generalized method of moments. Now, the essential step in the proximal causal inference approach is to find valid proxies ZT. In the synthetic control setting, ZT are readily available. So first, as I said, in a pool of candidate control units, not all control units go into the donor pool. So the control units not in the donor pool can serve as proxy units. In Abadi's analysis, they have 16 countries as the candidate control countries, but using their method, only 5 out of 16 countries have positive synthetic control weights. The other 11 countries may serve as the proxy variables. And sometimes a unit may be invalid control units and cannot go into the donor pool. For example, if the unit outcome is influenced by the treatment by interference, then it cannot go into the synthetic control unit, but it can still be a valid proxy unit. So now let's say we simply use the control units outcome that are not in the donor pool as the proxy variables. Comparing the standard OLS method, where we use the same donor units as the multiplied term to this residual error. But the different thing in the proximal causal inference method is that we multiply the control units, the proxy unit outcome to the residual term. And we can see that the later estimating function is unbiased. So now after we get estimates of the synthetic control weights, we can estimate the expected treatment effect by simply by the expected difference of the treated unit outcome and the synthetic control unit outcome. We can also decompose the difference of these outcomes into the mean and the residual error. So here the tau t can represent the deterministic trend, and the residual error RT can represent the residual error process. So by this decomposition, we can also use the standard time series method for estimating more flexibly the effect process, the time varying effect. For example, we may put a parametric model on the tau t, and then we can jointly estimate the synthetic control weights and the effect process by GMM, generalized methods of moments. Otherwise, if we view the treatment effect as random, we can also use either permutation inference approach or probability bounds approach to construct pointwise prediction intervals for this random treatment effect. So I conducted a simulation study to compare the different methods. I will skip the setting, but in this setting, you can see that the OLS method is severely biased, and even the standard synthetic control method is biased. In contrast, the proximal causal inference method is unbiased. Here, the CPI is the constrained proximal causal inference method, where we put additional constraint that the synthetic control weights are non-negative and sum up to 1. It is also unbiased. So going back to the German reunification analysis, we have West Germany, which is the treated unit, and 16 control countries. The outcome of interest is the annual per capita GDP, and the treatment of interest is the 1990 German reunification. So the original analysis also considered covariates, but because here we are just doing demonstration, we didn't match on the covariates. In the standard synthetic control method, 6 out of 16 countries were chosen into the donor pool. So we will put these 6 as the donor pool and use the other 10 countries as the proxies. So this is not the ideal method of selecting proxy variables because it is mostly data driven. We look at the results and then we select the variables. But here, the ideal method hasn't been established yet, so we are just using it as a demonstration. We see that, so here is the result. I only show the results visually. So different lines here. So here, the black solid line is the observed West Germany per capita GDP trajectory. And the other lines are different methods of estimating the potential outcomes. So the difference between the lines will be the treatment effect. And we see that the synthetic control method would estimate a higher treatment effect than the OLS method. And I also considered a placebo test. So here I arbitrarily set the treatment year as 1975, and we compare, and we use the synthetic control method, and we compare. So because in 1975, the West Germany didn't actually have the treatment, so the causal effect should be 0. But the OLS method has very unstable post-treatment trajectory, while the other methods all perform similarly. So this suggests that the OLS method may be biased and give you unstable results, but the proximal causal inference method and its constrained version give you ideal results. So the take-home message of this part is that the OLS-based synthetic control methods can be inconsistent if the pre-intervention fit is imperfect. And the proximal causal inference method provides a formal framework to reason about identification, estimation, and inference in the synthetic control setting. It also has multiple extensions. So for example, it can incorporate serial correlation of the error terms. It can incorporate stationary or non-stationary latent factors. It also has the version of adjustment for additional covariates, and it can be extended to binary and count outcomes using confounding bridge function approach. The proximal causal inference approach also opens a door for time series approaches for analyzing time varying treatment effects. Any questions? Okay. All right, so that's it.
Thank you for the presentation. For the intervention fit that you say that is imperfect, how do you quantify that the intervention fit is imperfect between the treatment and the control?
That's a good question. Yeah, I guess you can only quantify it empirically, like you can compute the mean absolute deviation or the mean squared error. But there is not a clear cutoff of whether the fit, the match is perfect or not. So the goal of fitting on the outcome, if you think about it, it's coming from a prediction point of view. You think you try to match on the pre-treatment outcomes and make sure your prediction is good. But if you go back to the causal mechanism, it doesn't really make sense. Does that answer your question?
Yeah. Well, there is not clear cut on how to define it.
Yeah, there are no clear cuts, but basically you just compare the magnitude of so for example, mean absolute error and the outcome and see if the mean absolute error is like substantially large.
How do you select because you synthetically you need to select for example, in the example you showed us, I guess for example, you have two choices. One choice, if you can use all the countries, all the European countries, you can also select all the countries in Western Europe. How do you select the targets?
Yeah, thank you. That's a very good question. So the question is how to select vulnerables in synthetic control. The recommendation is that you select the control units that are sufficiently similar to the treated unit during the pre-treatment period. In the data sets, the common approach is that you usually match on other covariates, and you just evaluate the closeness of the pre-treatment covariates and the outcome, and only select those that are similar enough. So as you said, the European countries, the West European countries might be a good criteria in this specific example. Here, what we did is we did the synthetic control method using all the countries at first, and we select those countries with large weights, and we exclude those countries with essentially zero weights.
I have a question about the part of the survival. So, doing that, you also have measure variables that the assumption of conditional independence between sensory and survival fails as well, and you want to use proximal methods also to adjust for sensory, for unexplained sensory, unexplained what do they call it? The sensory mechanism is not enough.
Oh yeah. So the question, yeah. So there have been works on common factors, common causes, unmeasured common causes for the right sensory and the outcome. I think it's also using proximal inference. It's also by Andrew Lin and Eric. The paper is positive. Yeah. Non-ignorable sensory.
I'm not familiar with that.
Mhm.
Well, if not, let's thank our speaker once again.
Thank you, everyone.
Thank you all for coming. Yeah, great. Let's close this. There was no questions on Zoom.
Okay.
I was monitoring Zoom. Stop share.